Okay, so today we're doing 7.5c, and for example 1, you find an old clock in the attic. And it's an analog clock, like that one. So it doesn't have an AM or a PM. It's not military time. Okay, so then obviously it stopped, right? Because the batteries have run out long ago. It's been in the attic for years. So the question is, what are the chances that the clock stopped at a time between 3:30 and 6:30? What are the chances that the clock stopped at a time between 3:30 and 6:30? So I'm going to do this problem 3 different ways. 2 of them are valid and 1 is not. So first of all, for method 1, between 3:30 and 6:30, there's a 3-hour time span, right? So the chances that it stopped in there are 3 out of something. So 3 hours that it could have stopped to hit between 3:30 and 6:30. And then overall, there's 12 total hours, right? Because there's no AM or PM, so there's not 24 hours. So the chances are 3 out of 12 that it stopped between 3:30 and 6:30. So the correct answer to this problem is 1/4. So 3 total hours between 3:30 and 6:30 out of a 12 total hours that could have stopped. So that's why the chances are 1/4. Okay, now some people think of it this way, though. This is the not very productive way to do the problem. How many times are there between 3:30 and 6:30? Infinitely many, right? Because there's 3:31 and 3:31 and 1 second, and 3:31 and 1.5 seconds, and 3:31 and 1 3/4 seconds. There are infinitely many times between 3:30 and 6:30. So the numerator of the fraction should be infinity, because there's infinitely many times between 3:30 and 6:30. And then there are also infinitely many times between noon and midnight. So the denominator should be infinity. But in some sense, there's more down here, right? There's more times between noon and midnight than there are between 3:30 and 6:30. But in both cases, they're infinity. So this doesn't really get you anywhere. Infinity over infinity, I don't know how to do. I don't know what that is. Apparently it's 1/4. But yeah, that doesn't really work. Okay, so for method 3, we're going to use the new method that we're going to learn today. And so we're going to use what's called a probability density function. Okay, so I'm going to graph a function. And on the bottom is going to be the time in hours. So there's 1 o'clock, 2 o'clock, 3 o'clock, 4, 5, 6, 7, 8, 9, 10, 11, all the way up to 12 o'clock, right? And just for simplicity's sake, if it's 12:15, we're going to call that 0 and 15 minutes. So 12:15 is going to be graphed there. We could just as easily put it over here, but I'd rather go 0 to 12 than 1 to 13. Just makes more sense to me, but you could do it either way. Okay, now what we're supposed to do here is make on a probability density function, the chances are area. Okay, so on a probability density function, the probability is area. So on a probability density function, the probability is area. And you do abbreviate probability density function PDF. And this is older than the modern day PDFs. So for me, when we started calling documents PDFs, that was strange because to me it's a probability density function. Now for you guys it's going to be the other way around. You have an idea of what a PDF is, and now you have to have this other idea of what a PDF is, probability density function. Okay, so I need to set up this function so that the probability is area. So I need to set up this function so that the area underneath the whole thing is 100%. Because the chances that the clock stopped somewhere is 100%, right? So it could be anything between 0 and 12. So how can I make the area from 0 to 12 be 1? I need to make the height be 1/12, right? So if I graph a function that has a height of 1/12 between 0 and 12, the reason I chose 1/12 is because now if I take the area, I get 1, which is 100%. So now the probability density function is having the probability be area. Okay, so then, if I want to know what are the chances of the clock stopping between 3:30 and 6:30, I just have to find the area from 3:30 to 6:30 underneath my PDF, which I guess I'll call f of t dt. And that's easy on this problem because it's just a width of 3 times a height of 1/12, which is 3/12, which reduces to 1/4. So we already knew 1/4 was the right answer, but now we're making up this new concept of area being probability. And that's what a probability density function is. It's a function under which you take area and get probability. Okay, so using this idea, what are the chances that the clock stopped at exactly 3 o'clock? What are the chances that the clock stopped at exactly 3 o'clock? So we're supposed to find area, right? The area from what to what? 3 o'clock to 3 o'clock. So area from 3 o'clock to 3 o'clock, what is that? 0. And people don't like this. They don't like that the chances, they think there is a chance that it stopped at exactly 3 o'clock. But I would say, hey, if you think it reads 3 o'clock, maybe it actually reads 3 o'clock and 1 nanosecond. Or maybe it actually reads 3 o'clock and 1 second. So the chances that it reads 3 o'clock are extremely tiny. You can at least agree with me on that, right? Because how many times are there that it could hit? 1. And how many total times could it hit? Infinity. So at least you've got to agree with me that the chances are 1 out of infinity, which is extremely close to 0. So either we're just arguing between something that's extremely close to 0 versus something that's 0. For practical purposes, we want the area to represent the chances. So we're going to say that the chances are 0. And you could argue with me that it should be 1 out of infinity, but for practical purposes, we're going to call that 0. All right, so the chances that it stopped at exactly 3 o'clock are 0. And that I'm a little uncomfortable writing 1 over infinity. It's not really a number. So I'm going to erase it just because I'm on tape. But yeah. All right, so now we're going to get the official definition of a probability density function. A probability density function is a function that meets two requirements. The first requirement is all of the heights have to be bigger than or equal to 0. So let's go back to this probability density function here. What are the heights between 0 and 12? 1/12. So are those bigger than or equal to 0? Yes. Okay, what's the height down here at like -1 o'clock? What are the chances that it's going to hit -1? 0. So we need the height down there to be 0, right? So that the area is 0. Is that bigger than or equal to 0? Yes. And above 12 o'clock, this is not a military clock, so it's not possible to read 13 o'clock either. So that the height up there would be 0 as well. So this PDF hits that requirement, right? Sometimes it's 1/12, which is bigger than 0, and other times it's 0, which is bigger than or equal to 0. So we're good there. So that's, and then the second requirement is that the area from -infinity to infinity underneath the function needs to be 1. Is the area underneath this function 1? Yeah, because down here it's 0, up here it's 0, and then in between 0 and 12 it is 1, because it's 12 times 1/12. Why does the area need to be 1? Because that's 100%, right? So you want the chances of anything happening to be 100%. So that's why this area needs to be 100%, aka 1. Okay, so that's the official definition of a probability density function. And the practical application of it is, then to find probability, you just take the area underneath it. Okay, so over the weekend, there was a flight from Syracuse to Philadelphia, and there was a woman sitting next to a man who was sort of dark-complected with dark curly hair, and he was writing furiously in his notebook a language that she did not recognize. So she got a little scared, and she notified one of the flight attendants, and they held the plane for 2 hours and questioned him. It turns out he's Italian, not Middle Eastern, and he was writing math. She didn't recognize the mathematics, the strange language of mathematics. They questioned him for 2 hours. Now, he did say that they were polite, so that's good. The authorities that questioned him were polite and just checked out the plane and checked everything. Mathematics is a strange language, as you know. Some of the time when I'm writing mathematics, you're a little jumpy as well. So we can understand this story, why people are a little uneasy. Especially, we understand why people are uneasy right now because of what happened last week. So I'm not saying this to downplay anybody. I just thought it was interesting because of the mathematics being not recognizable. So, yes. Okay, so next we're going to talk about a normal distribution. A normal distribution is a set of data is normally distributed if, so what we're defining here is what it means to be normally distributed. So a set of data is normally distributed if, and it needs to hit 2 requirements. Number 1, the chances of being above average need to be equal to the chances of being below average. the chances of being above average are equal to the chances of being below average. Now, at first glance, this seems like it should always happen. Doesn't it kind of seem like the chances of being above average should be the same as the chances of being below average? But that's not always true. Let me give you a really simple example. Let's say you have 3 people, and one of them makes $1 million, and the other 2 make no money at all. The average salary between the 3 of them is $333,333, right? $1 million divided by 3. So there's one person who's above average, and there are 2 people that are below average. So in that scenario, it's not equally likely to be above average as below average. But if it does happen that it's equally likely to be above average and below average, then this requirement is met, and maybe it's a normal distribution. But there's a second requirement for a normal distribution. The second requirement is that the chances are higher that you are close to average rather than far away from average. The chances are higher to be close to average rather than far away from average. I'm not sure I said that the best way, but what I'm trying to say is that more people are close to average than are far away from average. Or more of the data is close to average than far away from average. Doesn't have to be people that you're taking the data on. Okay, so let me draw you a curve that might fit these requirements. So here is a curve. And we need a letter for average. So the traditional letter for average is the Greek letter mu. Yes. Thanks. So mu is the mean, which is also called the average. And here's a graph. So remember, this is a probability density function, so the area under this curve is the chances, right? So if you want to find the chances of being above average, you would find the area from here up. And if you wanted to find the chances of being below average, you'd find the area from there down. So are the chances of being above average the same as the chances of being below average on this graph? Yes, so criteria 1 is met, right? The chances of being above average are the same as the chances of being below average. Okay, but is it more likely to be close to average as opposed to far away from average on this graph? No, because if you find the area close to average, that's less area than here, where there's more area, right? So the chances of being far away from average are higher than the chances of being close to average on this graph. So this graph does not meet both of those requirements. It does meet the first one, but it doesn't meet the second one. Okay, so now I'm going to show you a graph that does meet both requirements, and this is the graph of the normal distribution probability density function. It looks like this. So the normal distribution is amongst the people called the bell curve. But statisticians call it a normal distribution more often. So if you've heard about the bell curve, this is it. Okay, so mu stands for the mean, but the bell curve could be more spread out. It could look like this instead, sorry. It could be less high in the middle and higher towards the ends. This is still a bell curve. It's still got equal area above mu and below mu, and it's still more area here than here. The discrepancy isn't as great, right? Here, there's very little area far away and a lot of area near. Here, there's less area near and more far away than compared to this. Okay, so this is both normal, so we need a way of measuring the difference between these. Here, the data is more spread out. Here, the data is more packed in. So that brings us to the concept of standard deviation. And standard deviation is a statistic that measures how spread out a set of data is. A statistic that measures how spread out a set of data is. And there's a letter that stands for the standard deviation. It's the Greek lowercase sigma. So we use mu for the mean or the average, and we use sigma for the standard deviation. You've seen a capital sigma before. That's a capital sigma, right? You've seen it too often. So this is the capital sigma, that's the lowercase sigma. Okay? All right, so here, the data is less spread out. So this will be a smaller sigma. Whereas here, it's more spread out. So this will be a larger sigma. Standard deviation, or sigma, measures how spread out the data is. So if it's more spread out, it'll be a larger sigma. If it's less spread out, it'll be a smaller sigma. Okay, so what I'm going to show you next is the function, f of x, that will graph this shape and this shape. So I'm going to show you the probability density function for a normal distribution. The other probability density function we saw was easy, right? It was just a 1/12. F of x equals 1/12. But this one is a little more complicated because it's curvy. So this is the probability density function for a set of data that is normally distributed. So what I'm about to show you is the f of x that'll graph the bell curve. Okay, so what it is it's 1 over, I think it's 2 sigma. No, just sigma. 1 over sigma times the square root of 2 pi. What does sigma stand for? The standard deviation. So this will be a number on a particular problem, but it'll change from problem to problem. This is a number that doesn't change. It's pi, right? So far we've just got numbers. And then it's got e in it. Okay, so you can understand why a mathematician would really like this formula. Because it's fun enough if a formula has pi in it, and it's also fun enough if a formula has e in it. But if it has both, wow, that's a lot of fun. to have both E and pi. And it's kind of interesting that that pops up on this kind of a curve. Okay, then it has a power on it, and the power is kind of complicated. It's a fraction, power, and it's negative x minus mu squared all over parentheses 2 sigma squared. All of that is the power on E. We're just going to math 9 it. Because the antiderivative is pretty complicated. Okay, so that brings us to example 2. And in example 2, so for part A, we're going to write the PDF for a normal distribution with mu equals 75 and sigma equals 10. Okay, so mu equals 75 means the average is 75. So it could be that this is a test, and the teacher calculated the average, and the average came out, average score was 75. And then the standard deviation equals 10. That means that if you go 10 below 75 and 10 above 75, a nice chunk of the students scored in that range. So from 65 to 85, a certain percentage scored in that range. Now, on a different test, maybe the standard deviation would be 20. And so then that means from 55 to 95, the same chunk scored between 55 and 75. So in the first case, the standard deviation is only 10. So a good chunk of the students scored between 65 and 85. And if the standard deviation was 20, the same chunk, same percentage, scored between 55 and 95. Because it's more spread out when it's a bigger standard deviation. Okay, so anyway, if we're going to write the PDF, all we have to do is use this and put 10 in for sigma and 75 in for mu. So it's just, you just go off of this and write it down. So it's f of x equals 1 over 10 times the square root of 2 pi times e to the power of negative x minus 75 squared. So I just put a 10 here and a 75 there. And then in the denominator, just be careful. It's not, there are parentheses. So if there weren't parentheses, it would mean 10 squared and then times 2, right? But since there are parentheses, it means 2 times 10 and then squared. So 2 times 10 is 20, and 20 squared is 400. So I'm just going to go ahead and put 400 in that denominator. So we don't have time for this today, but when you do your homework and tomorrow during class, if you're here, you'll type this into your Y1 and you'll be able to graph it. And it looks like the bell curve. Okay, so now for part B, we're going to find the probability that a student scored between 65 and 85. I left out the word Find the probability that a student scored between 65 and 85. So how do you find the chances that something happened? Area under the PDF, right? So all we got to do is take the integral from 65 to 85 underneath this thing. I don't want to write this down again. So I'm just going to write f of x dx. So my advice when you do your homework is put this in your y1, right? And then math 9 y1 from 65 to 85. So you don't have to write it, so you don't have to type it all in again. And then if you look at this graph and you've got a bell curve, you know you have it typed in correctly. So then you'll know you'll get this integral correct as well. And this comes out to about 68. It comes out to about 0.68, which means 68%. And it's a fact that if you're one standard deviation away from the mean, so 75 is the mean, right? 65 to 85 is one standard deviation. If you're within one standard deviation of the mean on a normal distribution, that's always a 68% chance that someone scored there. So then if the standard deviation was 20 and you integrated it from 55 to 95, you would also get 68%. Because there's always a 68% chance of being within one standard deviation of the mean. Okay, so last Wednesday, some of us had to ride a bus to the junior high, right? Some people had their cars, some people had their keys, but some didn't. I had to go ride to the junior high. I had my keys and my car, but they made me stay with the students. Okay, so I rode the bus to the junior high, and then while we were at the junior high, there were a few calc students, and the AP Calc test was Thursday, right? So there were a few uneasy students saying, hey, what's going to happen with the AP Calc test? And they were telling me that their notes were in the school and their calculators were in the school. Well, the notes I wasn't too concerned about because I knew that they had studied a lot over the last 4-6 months, and so I didn't want people staying up really late studying Wednesday night anyway. So I was like, don't worry too much about your notes. But calculator, I get that. You know, if we can't get back to the school, we need to have a calculator. So I said, you know, try to borrow one from a sister or a neighbor or something. Make sure it has batteries, etc. But in the meantime, I'll work on it as well. I'll see if I can track down some calculators. But I figured they would let me at least, back into the school later that day so I could find some graphing calculators here and take them over. But then there was a note found at the junior high while we were there. And so then we had to start evacuating the junior high. And that made me a little bit more nervous. I was thinking maybe this is getting a little out of hand. Things are starting to fall apart. If you read Chinua Achebe. So anyway, things were falling apart. And I was thinking maybe we're not going to get back into school today. And maybe we're not going to get back into junior high today because this is escalating a little bit. So the junior high students are walking this way, but some are going to their lockers this way, right? So I said to a 7th grader, I said, hey, do you know where the math rooms are? And he was like, yeah, I'll take you there. So I'm walking with some junior high, and he takes me and I find Mr. Higgins, right? So I say, kids are evacuating. Mr. Higgins is like, okay, trying to keep everybody calm. Mr. Higgins, yes. Do you have any graphing calculators? And he was like, he was kind of taken aback. He was like, yeah, I got some. And I said, can I have them? He was like, well, then he started asking questions. He's like, why do you need these? And I said, well, the AP Calc test is tomorrow. I have some students that left their calculators in the school. Just in case we don't get back in, I'm going to take some to them. So I said, yeah, no problem. So he gives me this bag of 30 calculators. Here, let me go get the bag. So here's my bag of 30 calculators. And I was trying to estimate how many people maybe forgot their calculator or had it in the school. And I was thinking, well, there's 70 AP Calc students. So maybe half. So I wasn't sure 30 was enough. So I went next door to Mr. Higgins' room and got a box of like 20 more. So I've got a bag of 30 calculators and a box of 20 or so calculators. And then I've got my bag, right, and my lunch, which I smuggled out of the school. And I was like walking out of the building. And I got to auditorium, and at that point they told us, hey, the high school kids that are still here, they're going to have to walk to the fairgrounds. And teachers, you need to walk to the fairgrounds with these students. And I said, I can't carry all this to the fairgrounds. So I sent Rachel, my wife, on ahead. I said, you go ahead and walk to the fairgrounds. I'm going to figure something out. So I walk. Now everybody's coming this way. No one's going this way, right? So I walk past the guy with the M16 and past Mr. Butler back towards the math rooms, right? And everybody else is coming this way. I've got a black bag full of electronics, right? Mr. Butler says, hey, Mr. Early, are you going to do some math? And laughs. And I'm like, there's a guy with a huge gun standing right there. Be quiet, Mr. Butler. Do not attract attention to me. I'm already going the wrong way with a black bag. So anyway, I get past him, luckily, and I find Mr. Higgins. And I say, Mr. Higgins, you got to put these in your car. Because I didn't have a car, so he put them in his car. And then I'm walking back past the guard without the black bag, looking even more suspicious, now empty-handed. But he didn't stop me either way. That's how dedicated I am. Nobody used one.